Another way we can describe a function is by giving its graph. And just like functions that are given in any other form, we can do function algebra on functions that are described as graphs. So here we have the functions f, g, and h. And we don't have expressions for these functions, we just have the graphs. But we can evaluate functions from their graphs. And so if we want to find f plus g of 2, we'll take f of 2 plus g of 2, and then to find f of 2, we'll find the x-coordinate 2 on the graph of f. We'll go and find the point on the graph that has that x-coordinate. We'll see that this is the point 2, 2. So f of 2 is 2. And then to find g of 2, we'll go to the graph of g. We'll find x equals 2. We'll find the point on the graph that has that x-coordinate. We see that this is 2, negative 3. And so g of 2 is negative 3. To take f plus g of 2, then, we're taking 2 plus negative 3 is negative 1. Okay. Next, we want to take g minus h of 4. That'll be g of 4 minus h of 4. So to take g of 4, we go again to the graph of g. We find the point with x-coordinate 4. We see that that's right on the y-axis. So this is the point 4, 0. G of 4 is 0. H of 4, we go to the graph of h. We find x-coordinate 4. Find the point on the graph with that x-coordinate. We see that this is the point 4, 3. So h of 4 is 3. To take g of 4 minus h of 4, then we're taking 0 minus 3, which is negative 3. G minus h of 4 is negative 3. What if we want to take f times h of 1? Well, that'll be f of 1 times h of 1. So to find f of 1, we find x-coordinate 1 on the graph of f. We go up and we find this point, 1, 1. So f of 1 equals 1. What about h of 1? When we go to the graph of h, we find x-coordinate 1, and we see something weird happening on this vertical line. We see 2 empty dots with x-coordinate 1. We remember that empty dots represent a point that isn't on the graph at all. There is no point on this graph with x-coordinate 1, which means that that h of 1 that we want, that's undefined. If h of 1 is undefined, that means the product, f times h of 1, is also undefined. Okay. Well, let's see if we can do any better with f over h of negative 2. That'll be f of negative 2 over h of negative 2. So to take f of negative 2, we go to the graph of f. We find the point with x-coordinate negative 2. Oh, good. There is a point like that. This is the point negative 2, 2. So f of negative 2, that's positive 2. What about h of negative 2? We find the point with x-coordinate -2. Oh, good. We see that there is a point on the graph with x-coordinate -2. This is the point -2, 1. So h of -2 is just 1. F of -2 over h of -2, that's 2 over 1. It just works out to 2. Okay, one more. H over g of 4. That'll be h of 4 over g of 4. To find h of 4, we go to the graph of h. Oh, we've already found h of 4 earlier. Cool. H of 4 is 3. Looks like we found g of 4 earlier as well. G of 4 is 0. So h over g of 4 is 3 over 0, which is nothing. We can't divide by 0, so h over g of 4 is undefined. So notice in this last example, g and h were both perfectly well defined, but because we can't divide by 0, h over g was undefined at that point. In addition to just calculating these functions, we can also find the domains looking at the graphs. So these are the same 4 functions, f, g, and h. But now rather than just evaluating the functions, we're going to be considering their domain and range. And in fact, we're only considering the domain here. So we're imagining taking each function and flattening it into the x-axis only. We're not interested in the range right now, so we're not going to look at the y values. For f, our open dots come down to the x-axis like that, and then our domain extends off to the right, and it extends off to the left. So the domain of f is everything except for this gap in the middle. We'll have -infinity up to -1, and -1 is included, union with +1 up to +infinity. +1 is also included. So that's not bad. And the domain of g is even easier, right? G covers the entire graph, and it extends off to the left and to the right. If we squish this into the x-axis, we're going to just cover the whole thing. In interval notation, this is -infinity to infinity, or we can say all real numbers. As for the domain of h, well, the good news is h is entirely contained in the bit that we can see. So we imagine squishing this into the x-axis. We end up with an empty circle at -4 and at 1, cover everything in between. And then another empty circle out at 5, cover everything in between there. Our domain of h is going to go from -4 up to 1, and then from 1 up to 5. And that's it. Okay, so those are the domains of our basic functions. If we add them together, we want the intersection of those domains. So I'm going to just sketch a number line, and I'm going to work from the domains of f and h that I already wrote down. It looks like I'm going to be interested in the numbers -4, -1, 1, and 5. The domain of f goes from -1 off to the left, and then from +1 off to the right. The domain of H goes from -4 up to 1, then from 1 up to 5. So let's look at the intersection here. Well, we don't include -4, but then we go up to -1 and include -1. The domain of F includes 1, but the domain of H doesn't. So the intersection doesn't. But then we continue up to 5, and 5 is also not included. The domain of F plus H, which is the intersection of the domain of F with the domain of H, is the set from -4 up to -1. -1 is included, union with the set from 1 up to 5. Okay, what about G over F? Well, the first thing we notice is that F is never 0. No matter what x we have, f of x is not 0. So the domain of G over F is actually going to be just the domain of G intersect the domain of F. And even better than that, the domain of G is all real numbers. So we're really just looking at the domain of F. So this one ends up being very easy. So -infinity up to -1, union with 1 up to infinity.